The next speaker, Alexei Davydov. He will talk on the Riemann centers of finite groups.
I'd like to join the chorus of thanks to the organizers. It's a really very interesting conference and a very inspiring place. Oh, yes, that's right. And yeah, everything is superb. Well, the weather, though, but it's probably beyond capabilities of organizers. So I was thinking about using the class of fusion, braided fusion categories as Greenfield centers of finite groups, which is an easy class and easy to work with, but has enough features to see the general theory. Just to link with the main stream of the workshop, C-star algebras, as I imagine Greenfield centers related to finite groups, they appear as symmetry. So if you look at orbifold construction conformal with theory, say presented in algebraic framework, you do this orbifold with something which is holomorphic. So for example, something coming from a self-dual lattice, say E8, and you take a group of automorphisms. The whole group is of course infinite, but you take a finite subgroup, you do the orbifold, you end up with this sub-theory, conformal net, chiral conformal net, which will be not holomorphic anymore. So it will have interesting representations, and as I understand, in algebraic conformality theory, it's a theorem that it will be still rational, and the category will be semi-simple, easy, and the category will be what is called this twisted Greenfield center. So this is the first. Yeah, we'll try to illustrate as much as I understand of the current state of these affairs, pointing to places. Although this is the simplest example, one of the simplest possible examples, there's still so many things which are unknown, at least to me. And the first such is, yes, we do the simple, well understood construction. We end up with this Greenfield center, but then there is some unfortunate, some sort of a nuisance. This flicker cycle pops up, and there is no way of predicting at the moment of for which groups this flicker cycle will be non-trivial and of what it will be. So this is the first question mark. This is the first exercise, take-home exercise. And yeah, so that I will try to suppress, this twisting in a Greenfield double. I'll try to suppress talking about Greenfield doubles because it will inevitably make formulas more complicated, but not change really the essence of them. So I won't talk much about twisting, but we'll just talk about the untwisted case, which is easy. So this is the easiest example of a braided, well, one of the easiest examples of a braided fusion category, but maybe it's better to start with the easiest example of a fusion category. So this is the example of a fusion category. Of course, it's just vector spaces, but next easiest, it's vector spaces with a little bit of structure. And to make the fusion the easiest, this structure better be just graded. So we'll just start with a group, and everything will be finite. There'll be a finite group. Yeah, I have to stop and ask a question. So it's supposed to be a workshop on C-star algebras and tensor categories. Should I define what tensor categories are? Should I draw these pentagon axioms just once during this workshop? No. Okay, good.
Too scary. Too scary.
Okay, yeah, I agree. There's a finite group, and again, it's the easiest category, which is fusion, which means in general semi-simple with finite number of simple objects, or finite dimensional forms, all that, and then all objects are dualizable, they have duals. Well, here, yeah, I'm going to suppress this twisting, this nuisance, but it's just one indication how naturally it pops up in this very example. So we just look at the category of G-graded vector spaces. I will still need this, although most of the audience are specialists, I'll still need this as an anchoring point for, I guess, indicating how the computations are usually done. So the category of G-graded vector spaces, just a typical object is a vector space, finite dimensional with decomposition to direct summands labeled by group elements, and then the tensor product is just the tensor product of vector spaces. All we need to write is how we grade it, and the degree G component, of course, it's a direct sum of homogeneous components, and the condition is that their degrees multiply into the required element G here. So yeah, you could see how it is semi-simple, what are simple objects, what is a fusion on them, and so why are they all dualizable. This alpha is a freedom in choosing this associativity constraint for the tensor product. It's a part of the story in category theory. You can't say something is equal to something else. People will look at you in a funny way. So you have to say that something is isomorphic to something else. If you suppress this freedom, you can't do that, but if you suppress it, you will create problems somewhere else. So the general message is better keep everything as free as possible, and then this associativity will be just natural isomorphism, collection of isomorphisms between tensor products like that. So on elements, I will choose my elements homogeneous on elements of these vector spaces. It's all with contents, all concrete. My associativity just does the rebracketing of this bit, and an unobvious bit is just to multiply by phase, by number, by an invertible scalar. And this invertible scalar will feed on a triple of group elements, which are just the degrees of these homogeneous vectors. And then you could see that this pentagon axiom, which I'm not supposed to draw, is exactly a 3-cycle condition. And then the standard condition is that with respect to monoidal product, the category is called monoidal, which is a part of being tensor and fusion and everything, is to have the identity object. And identity object is just usual identity rule with respect to the operation, which is called the tensor product. And this identity object has to behave coherently with respect to all the constraints on the category, like associativity. So the 3 cycles we get usually are normalized, meaning that if we evaluate them on the identity of the group in any of the arguments, we will get just 1. So that's a nice technical condition. Okay, so this is a category of graded vector spaces. It's not braided, because I'm not constraining my group to be anything abelian or something like that. So it's just as general as it can be. Any finite group will do for that construction. To have something braided, I have to have commutativity, sort of commutativity on my tensor product, and it's not. But there is a construction which takes a monoidal category in general and produces a braided monoidal category. And that's this Drinfeld or monoidal center construction. So the construction is just a beefed up version, a categorification, what is called, of the natural construction of the center of something. So if you have a monoid, something where you can multiply, and it works in an associative way with unit. So then you can look at all elements which commute with everything else. And that's a center. And the monoidal center is almost the same, but commutes, uses the equation sign, which is forbidden in category theory. So you say that one side of the commutativity equation is isomorphic to the other side of the commutative equation, and you remember which way it is isomorphic to. And then you ask for that way to be self-coherent. So I'm not writing the definition of center, or should I? Okay. So that's the story. You just ask for this half braiding, it is called, to be self-coherent, and then you end up with a nice category which is braided monoid. So that is a construction which takes any monoidal category, or let me call it S, and produces a braided monoidal one, which is called this Greenfield center. And again, the concept, the objects of these are pairs, something in S, and then the collection of these commutativities with the rest of S. So these half braidings are natural collections of isomorphisms. So obviously we have, as in classical situations, center sits inside what we compute the center of. And we still have a map or a functor from the center to the original thing. But it's no longer inside in any way, because what we do, we forget about the way we braid with the rest. And actually, it is a natural measure of sizes of categories. You can't just count the number of objects, because it means nothing. The same categories, equivalent categories, can have drastically different objects, but the good measure of size, especially in the tensor framework, is called the dimension, categorical dimension. So in this measure, the center becomes twice as big as the original thing. So it's kind of totally counterintuitive behavior, but yeah. Okay, so what happens? What happens if we do the center construction? And this is really a nice exercise. If you didn't have a chance of doing that, I really strongly encourage you to do, because by just doing it, you will feel so much more about tensor categories. Just computing what the center of these graded vector spaces, I'm suppressing the associator, is. I'll just give you the answer. So the answer will be, of course, the first component of an object in the center is an object in the original category, so it's just a graded vector space. I'll call it Z. And the second component is natural collection of isomorphisms. And what it can be transferred into the minimal amount of information you need to know about this natural collection of isomorphisms is how they behave when you evaluate them on simple objects. It's how Z commutes with simple objects. And that can be translated into a different structure, action of G. But this action will not preserve the gradient. It will twist it in a conjugation way. And that's it. So I still owe you the braiding, because that's supposed to be the braided category, and the braiding is like that. So it's an isomorphism between tensor products of two objects, two such objects. And I will just write it on elements, and I take an element in degree f, and this is whatever. Don't care. So when I braid, I will just do the formula. So that's the formula which corresponds to the natural braiding on the center. A very easy category, a very complete category. You can do anything with it. You can see, first of all, that this is a semi-simple category. Well, with some minor conditions that the ground field, if it's complex numbers, then there's no condition at all. For any finite group, it will be semi-simple. You could see what are simple objects, how many. And yeah, how many simple objects do we have here? Again, it's a nice exercise. That's why this such a nice class of examples. So say what's called the rank of the category, number of simple objects, or just how we parameterize simple objects. What do they correspond to? It's somewhat similar to now representations of G rather than just vector spaces graded by G. So when we count, when we label irreducible representations of a finite group, what we do, we just look at the characters and irreducible characters and one-to-one correspondence with irreducible representations. And these characters are nothing but class functions. They are functions on conjugacy classes. So we end up with a statement that there are as many irreducibles as conjugacy classes. So here it's somewhat similar. You still can define characters, and there will be functions on pairs of elements. You can see why, because you have two structures labeled by group elements. So you could just define a character by computing traces, still as a usual representation theory. The character of V will be computing traces of operators labeled by G on vector spaces labeled by, or rather operators labeled by F on vector spaces labeled by G. So we have naturally we have two variables in the function. And yeah, now is the time to show. How can I compute the trace of something which is not an operator? Well, I have to restrict to pairs of elements for which my F is an operator on G. And the condition is that F and G compute. So this now this trace for objects of the center is a function, class function, still class function, but on pairs of commuting elements. That's the answer. It's not really an answer, it's a recipe. If you want to know how big your center is, just need to compute conjugacy classes of commuting pairs of elements. And yeah, everything comes in place. So this category is now whatever you like it to be. In conformal field theory, it's not just braiding which is natural. In rational conformal field theory, there is some extra condition on the braiding which is always present, and this is non-degeneracy. So what is non-degeneracy? And non-degeneracy, so in categorical terms, it's absence of elements which braid trivially. And yeah, that can be formalized by looking at the next center in line, but I would just rather say that what is trivially braided element, another name is transparent. So X in the braided category C is transparent if I better draw pictures. Let's see, my braiding of X, say in Y, will be represented like this. This string diagram will represent it. There is some meaning to it, but that will be just pictorial quick replacement of formulas. And then double braiding will be just this with this picture. So that means that I'm braiding X tensor Y into Y tensor X, and then I'm continuing with another braiding which ends up in the same tensor product X tensor Y. So you say that X is transparent if for any Y this double braiding is the same as doing nothing, is the identity on the tensor product of X and Y. The name was invented by Turaev, and the obvious reason just strings labeled by transparent objects are transparent. You can pull them through any other strings. So the totality of transparent objects inside your braided category is inevitably something where braiding becomes symmetry. And yeah, okay, I'll define it. So the symmetric center of any braided category is a symmetric category. And non-degeneracy means that we don't have anything interesting in the symmetric center. So the only transparent object is just identity object and its direct sums. So non-degenerate is no non-trivial transparent object. And what happens in conformal field theory that all braided categories are non-degenerate. So what usually it comes from is kind of a different piece of information. In the braided category, one can compute the so-called S matrix. Just take these double brackets for any pair of objects and compute the trace, because this is an automorphism. You can trace it up. Again, trace is defined because everything is rigid and even spherical in spherical in the braided case. So the collection of these numbers, if you just take pairs of irreducible objects, will be a matrix. And historically, it was the easiest information to access because in physics, what people saw are not really representations, but some easy to extract informations about them, like characters. And then these S matrix coefficients will come in naturally when you just look what happens with a character when you do modular transformations, modular group transformations. It happens preserve characters, so you move characters into linear combinations of characters. That's how these S matrices were originally computed, and they're always non-degenerate. For very natural geometric reason, but it must be left aside. So this non-degeneracy is the same as non-degeneracy of this S matrix. And there is a accompanying T matrix, so SL2Z, well, now is generated by a pair of matrices. One is traditionally called S and the other is T. And this pair of matrices always present for any modular category, for any category coming from conformal field theory. So what it really does is gives a representation of SL2Z on characters. Oh, sorry, yeah, in general, what we say instead of characters. So fancy name is just we take the Grothendieck group of the category, and because it is semi-simple, there is nothing but the free group generated by the classes of simple objects, free abelian group. And then S and T matrices are really operators on this. So we really have SL2Z action. On this free abelian group. And there's a very nice formula for that SL2Z action on level of characters. Because as with representations of finite groups, this, well, I said it slightly wrong. I have to complexify it. I have to extend my my group from just being free abelian group to just be direct sum of copies of complex numbers. So if I complexify this Grothendieck group of, let me abbreviate it to just Z of G to my Greenfield center. Again, character theory works well. Irreducible representations are irreducible characters. We have a notion of scalar product, so we can define irreducible characters, all that. And then complexified, it becomes just the space of characters. So there should be a formula for the SL2Z action on it, and it's very natural. You can guess pairs of commuting elements, 2 by 2 matrices with integer coefficients. So A, B, C, D, an element of SL2Z will act on a character by acting on the variables. So I'll just write how it acts on the variables. Just a natural way. So maybe inverted because I need to have the covariance working, so that's up to that inversion, that's formula. So yeah, this is so far just to illustrate how friendly, how comfortable this class of examples really is. But then the standard questions. These Greenfield centers, are they really totally controlled by this parameter which I used to define in this group G? So what if I take two different groups G? Will they be the same? How to see when I really get different categories. And the question becomes really much more complicated when we allow this twisting to hang around. So if we just have these two twisted infill centers, when are they the same? When are they being the same means that they are equivalent as braided tensor categories. And that is totally, totally natural question, but very non-trivial to answer. Well, there are answers, but they are, as usual, they are really prescriptions, and they are of kind of different level of practical sort of practicality. You can find them really not answers at all, but yeah, I'll try to give them. But maybe I will make a little detour and we'll talk about something before talking about equivalences between these categories. I will talk about something more generic, which is which seems to be more natural if we think about modular categories in terms of topological field theories. So it was believed for a long time, since Rishtikin and Turaev, it was believed that there should be a sort of equivalence between three-dimensional topological field theories in dimension 1 to 3 and modular categories. And it is true up to some specific adjectives, but it is essentially true. So it was proved or announced recently by a group of people, and it basically say that it is the same as to talk about topological field theories or modular tensor categories. So I will just try to use these geometric pictures to motivate my my next topic. And these geometric pictures already appeared in David's talk. Sorry, I'll just be repeating them again, but maybe we'll just say a bit more. So first is just what is the geometric meaning of just braiding, or what is the geometric meaning of tensor product really? But better start with dimension 1. So the story is like that. We just look at something geometric on one side, and it is configurations of little intervals inside the unit interval. And then each such configuration is supposed to give us an operation on our category. And as I said, we just need to look at basic configurations and see what they give us. So basic configuration, I forgot to say it, basic in what sense? Basic in the sense of composition. There is obvious composition of configurations. You can take one such, and you can take another, and then you can choose in the second one where you want to glue this one. So if I take some other configuration, like that, and I will choose this. It's all these holes are numbered, are labeled, and I will just choose this. I will scale it down, glue inside, and then gives me a certain structure of these configurations, which is called an operator. And it's called an operator because it operates on something, because it has a natural ability of operating on something. So if we take categories to operate on, we will end up with some structure on a category. This is just a neat way of encoding some structure on something else. So if this something else is a category, we will have the basic configuration will correspond to a functor from 2 copies of S back to S. So there is this middle term to be defined. It's how do you put together these 2 copies? So you can of course put cross, but that will be a very poor story. Much better is if all our categories are linear, and then we but abelian, and then we just use this Deligne tensor product. So for semi-simple case, if our categories are semi-simple, and this is just the simplest possible operation, we take 2 semi-simple categories. The Deligne product is just a category where simple objects are pairs of simple objects from the first from the second. So a very natural thing. And if we are in this one-dimensional little interval operator, we end up with with just one basic operation. So I haven't finished the geometric side of the story. We have topology on this on this sets of configurations, and we can talk about path inside these spaces of configurations. And what we will require is a path between two configurations should correspond to a natural transformation between the functors, which these configurations label. And this corresponding should eat away all the homotopies between paths. So then we just end up with very nice structure. We have one function to remember from two copies of S to S, and then one natural transformation to remember from three copies of S to S, and that is just associativity. So there's only one interesting homotopy after you're allowed to construct them modular. So only one interesting path in these configuration spaces if you look at that modular homotopy. So that's how you can encode just monoidal categories or tensor categories in this geometric way. And of course, 1 is not a special number, 2 is as good as 1, even better, even more interesting. So if we look at two-dimensional story, if we look at two-dimensional configurations of little squares inside a big square, yeah, so there's no difference between squares and circles. It's I just like them more because they're easy to typeset in text file. So then you again, the basic configuration is just this. It's still two squares cut out of my unit square, and then it still corresponds to the tensor product. And I still have this associativity. Well, on top of that, I have another interesting homotopy which works just for this tensor product. So this tensor product is denoted like that. And this homotopy is, well, all my holes, all my little squares are numbered, are labeled, because I need to know where, if I want to glue somewhere, where I'm gluing. And I can just swap them in one way or the other. I have to make up my mind, but if I do, I will have a homotopy, or a path, which will correspond to natural transformation. And you can see that it will be natural transformation between two tensor products. And then all the conditions you can get from geometry from the left-hand side, they will be just braided hexagons, two braided hexagons as standard conditions in a braided category. And it is related very much to a topological field theory. This is nothing but the genus 0 part of the topological field theory. The easiest, the most accessible part of the cobordism category we're supposed to have as a starting point of every topological field theory. So the more general way of comparing categories rather than just by equivalences is coming from that factorization algebra idea of Lurie, and very nice in geometric terms it is. So now I will just allow pictures which have again unit square and some configurations of smaller squares inside, but I will divide my unit square into two halves, and that's what David was talking about as well. So that now will allow me to have two braided modular categories. One which will be controlled by little squares appearing on the left, and the other which will be corresponding to little squares appearing on the right. So I'll call it C, and then this I'll call D. And then I have another sort of category hanging around which corresponds to this little square where I have two horizontal sides divided. So you could just, yeah, I'm colorblind, so I'm not using colors, but you could picture that this is sort of green and this is blue bulk, and then if your boundary is divided into two parts, one is green, one is blue, then it's something else. So this is another category. We could put it here, called S. And again, you can imagine all these compositions you could do with all these substitutions you could do with these configurations. So you could take, say, this picture and glue it inside a picture like that if it has a box sitting on the middle line. And what it amounts to is the following information. So you have this braided category C, you have this braided category D, and then you have this. So if I just erase this middle term, I will have something which starts with a copy of C, a copy of D, and produces me a copy of S. So the copy of object of S. So I have a functor. But as David was saying, just by looking at what you can do, how you can move this around using this braiding path, you could see that the way S and D are mapped into this, sorry, C and D are mapped into S, is that they naturally come with half braiding. So this functor factors through the monoidal center of S. And well, if we look at only the genus 0 story, that's as far as we can go. But in fully fledged topological field with algebra, we have to be able to interpret pictures like that. It's supposed to be a cylinder, cut, yeah, so separated by defect line, and having this red column right. And then the topological field here would say that this is an object in a tensor product of yeah, I have to change the orientation in D, and that corresponds to changing the braiding to the opposite. So I made another mistake. But yeah, so C box D should harbor this thing, which is an object, call it Z, but that is not just an object. It's a commutative algebra with a very special property. So that's inevitably a Lagrangian algebra. So that's supposed to be in my title. That's the second half of the title, which is missing. This is what is called modular invariant. Traditionally was called modular invariant in physics. Well, not quite, but what it should correspond to. So Lagrangian algebra I'll have to define now. And that makes, yeah, before I do that, I have to finish the story here. So that just the existence of this Lagrangian algebra forces this functor, or rather this functor, to be an equivalence. So maybe a short introduction. Why should, yeah, apart from just looking at CFTs with defects, why should I bother about Lagrangian algebras? If it is a conformal field theory, which I'm interested in, it's still of very practical interest, because so in conformal field theory we have this full state space of the theory, and then we have two, in rational case we have two chiral sectors. We have this holomorphic factorization, two chiral sectors, left and right chiral algebra sitting inside, and then the whole thing is just a finite direct sum of irreducible representations of these chiral things. So it's an irreducible representation of the product. Well, just here it is totally cosmetic, but we could here it doesn't make any sense. Sorry. Yeah, these are holomorphically holomorphically dependent fields, and these are anti-holomorphically, but it doesn't really make any difference. So it's more convenient. The answer becomes neater if we looking at this full state space as a representation of two chiral algebras simultaneously if we consider the second category with opposite braiding. So chiral algebras always produce, in rational case, always produce braided modular categories which are non-degenerate modular. So this bar really tells me that I have to flip the braiding and replace it by the opposite. And then this becomes an object in this category, and this object has some nice properties. So the total operator product expansion for all fields just gives me an algebra structure in this category, and this algebra is inevitably commutative. And the modular invariance property of that transfers into Lagrangian property. So Lagrangian algebras are very useful if you want to see all possible ways of starting with two chiral theories, building a full conformal field theory with these prescribed chiral sectors. So in particular, if we just look at what this object gives us in the Grothendieck decree, it should give us something which is modular invariant. So that's why the name modular invariance, because again, it was all done first in terms of characters. The character of this thing is just a product of characters of those reducible representations of left and right side, which it consists of, and then it's just a sum of products of reducible characters with some multiplicities, and the condition, natural condition, in this overall function is modular invariant. So that's how people work, physicists work computing them and classifying them and all that. But now we can do it in just using category theory and see for sure which are real, which are physical, and which are not. Because this Lagrangian property is relatively easy, so let me just define it. That's the second half of my title, modular invariance. But now I can add Lagrangian algebras. So what is Lagrangian algebra? Yeah, I can just start with a braided category, and non-degenerate it will have to be, but okay, Z is a commutative algebra. I don't need to define it. Okay, so first it is a commutative algebra. And with any commutative algebra, well, with any algebra, we can look at its internal modules. So it's not quite as it was in Corey's talk. We just look at all modules. Although I will use the same notation. Sorry. And this is the category of all modules over this algebra. So all right modules. And for a general algebra, this is all I can get. Just a category which happens to be a module category we see, but this is not the point. But for commutative algebra, I can just mimic the standard algebraic story and tensor my modules over my commutative algebra. So I have this tensor product over any commutative algebra, and well, I have to have a good category. I have to be able to form quotients, because when we tensor something, two modules over some commutative ring, we quotient by a certain relation. So yeah, I need to be able to quote. But in semi-simple case, there is no problem with quotient. So I have now a tensor category. And you might expect that it's supposed to be braided, but it's not. So that was discovered before conformal field theory found that all interesting. It was discovered just by pure algebraic investigation by Bodeparagis. It turned out to be just to the point. So in general, it is just not necessarily braided tensor category. What I mean not necessarily braided? So we do have a natural braiding in C, and we want to kind of lift it up to the modules, and it doesn't work in general because of the double braiding, because of the strings going around themselves twice. So to make it braided, we better look at nice modules. There is a way, what Bodhi discovered was a way of putting an extra condition on modules which will make the tensor product braidable with the underlying braiding. So this extra condition is called, now it's called locality. Prague's called it dyslectic. But local modules is really just down to the essence of it, because locality in quantum field theory is really what corresponds to this condition. A local Z module is the following thing. So again, I will use string diagrams for module structure. So a module structure, a right module structure will be something like that. So I have a string labeled by my module M, and then I have this algebra coming from the right and hitting and producing again module. And yeah, all my diagrams go from top to bottom. I'm a pessimist. Yeah, so majority go that way. But
bad guys.
Huh?
Bad guys.
No. I ended them. But okay, so locality is the following conditions. You just not much you can do using this picture and the braiding you have, and this is basically the only thing you can do. So you could do this. You could still have M starting here, then braiding with the algebra, and then finally meeting it here and then producing them again. And locality means that this is just the ordinary action of the algebra on the module. So a little miracle is if you look at the full subcategory of local modules, the underlying braiding will work there. It will become braided. Right, but what is it to do with Lagrangians? It's a bit long. Lagrangian is such that we do all this hard work and we end up with nothing. So Lagrangian means that there are no non-trivial local modules. Oh, well, non-trivial. Trivial is just identity. Identity module, which is just Z of itself, is always a module. It's now the identity object in this tensor category. It's always going to be local. But if we don't have anything else, if we just have this identity, this free module, and all free modules basically, the only local modules are free modules. But free in a very strong sense, just copies of Z. All right. So it looks like a horrible exercise, transforming something natural into something completely algebraic. But it opens the possibility of computing it. So now we can just take this notion and apply it to concrete examples like braided pointed categories or dream field centers of finite groups, and just compute which algebras. You can compute all algebras. Intercomposable algebras. In obvious sense, there is no submerged strokes here. And we can compute all commutative of those, and we can compute we can see which are Lagrangian. So the answer is the following. They are labeled by, I'll just tell you the labels. I don't think I need to bother you with how they are built, but it just labels. So Lagrangian algebras and I can bring the twisting back, since I'm not defining anything, so it's not that hard. So Lagrangian algebras in just one such category are in one-to-one correspondence with conjugacy classes of certain group theoretical data. Because, yeah, the only data we have at the start of the story is a group and a Tricker cycle. At the end of any question, any answer has to be just a group theoretical set of data and conditions. So the data we have is just a subgroup. and this little gamma is a two boundary on H which trivializes alpha when it is restricted to H. Yeah, if I would have an extra half an hour, I would explain more and how to get this in the least painful way, but I don't. Do I? Okay.
Is this classification of the isomorphism?
Yeah, so isomorphism, of course, on the left, and conjugacy. On the right. So that's a recipe of computing all full CFTs for orbifolds. Well, yeah, I have to slightly correct it because, again, I have to have a left and right halves, and okay. So if my left and right halves, they are holomorphic orbifolds, and they have these categories of representations being just some twisted double of G and then some other twisted double of Q. And I need to classify Lagrangian algebras here, but there's no difference because yeah, I can replace it by the infill double of the product, and the associator will be just this. So one particular usage of this information is to see what are called I forgot what they're called really. Just automorphism invariants, modular invariants which correspond to isomorphisms or automorphisms of the chiral halves, and they correspond to on the level of Lagrangian algebras, they correspond to autoequivalences. So this is one way of seeing autoequivalences. But maybe I won't spell out the answer. Maybe I will just, with the remaining 7 minutes, maybe I will just better give some examples of something which was rather unexpected. So there's going back to modular invariants, there is an always way of gluing together two halves which are the same. So if we happen to have the same left and right chiral algebras, it's kind of funny. It's the adjective for this is negation. It's non-heterodic type of conformal field theories. So if we happen to have the same category, there is always a natural candidate for a full conformal field theory. It's called the Cardy case, and now there is an ambiguity, historical one. So it is called sometimes diagonal modular invariant, sometimes charge conjugate modular invariant. So I'll call it diagonal. Well, Cardy is ambiguous. So it is always there. It corresponds to a very natural Lagrangian algebra, which again appeared first and wasn't really recognized as Lagrangian algebra. It was called tube algebra, but this is just an algebra which, as underlying object, is just a direct sum of all simple objects taken once. So I'm taking this isomorphism classes of simple objects, and I'm taking x on the left and x dual on the right, and there's a natural way of making it an algebra. And it will be commutative and it will be Lagrangian, so it will give us a what's called Cardy full CFT. So it's natural to expect that, well, this is a very constrained, very special, really, Lagrangian algebra, very spread over the two halves. So it's natural to conclude that the corresponding modular invariant really corresponds to just this case. So there's only one physical theory with the Cardy modular invariant. Well, it turns out to be not true. just this freedom of choosing the right group allows to construct examples of different Lagrangian algebras with the same underlying object. And moreover, the totality of them form a group. So this group, again, it's all related to symmetries of the category C. What basically is happening is I can take this special Lagrangian algebra, and I can take any symmetry in of my category, so any braided out equivalence, and I can just apply it to one side only of my delimited tensor product here. It will still be Lagrangian algebra, still be some full conformal field theory. And if f is such that it does something interesting with my braiding and all that, but it doesn't change my simple object, so to speak, then I won't see the difference on the level of characters, on the level of Grothendieckring. It will just look as the standard Cardy case, but as operator product expansions will have to be different. So that was believed to be impossible, such braided out equivalences which do not change objects. People, including myself, believe that they shouldn't exist, but surprisingly they do exist for dream field centers. And they form a group, obviously. You look at all braided out equivalences, and what you're really interested in is those which do not change the Grothendieckring. So the effect on the Grothendieckring is trivial. That gives you even not just a subgroup but a normal subgroup. And with all this detailed information, it's not that hard to see what the conditions, group theoretical conditions, have to be for such an equivalence. So I like to call them soft. And what they happen to be is they kind of an extension in its own right of something which was known before in mathematics. So luckily, people computed everything. So yeah, have to put it have to put this Bogomolov multiply in its own short exact sequence. So this is called Bogomolov multiply, and this is this is a subgroup of Schur multiply. And the Schur multiply is nothing but the second cohomology group with coefficients in invertible scalars. And the kernel of just taking restrictions to all abelian subgroups. So we look at cohomology classes which trivialize on every abelian subgroup of a group. That again, it looks like if you remember what you really classify second cohomology by, it looks like it should be trivial, but it is not. It's an art to produce examples, but they exist. And then there is another term. Well, naturally, you can kind of look at what happens with yeah, okay, I'll just write where it goes. So it's automorphisms of G. You kind of you look at how these things act on G. There is a natural homomorphism into the group, and the kernel is just that thing. So yeah, what happened is interesting examples of this very strange soft autoequivalences can come from both sides. They can be non-zero here, it can be non-zero here. I will just say what is the smallest kind of known example when we can have a conformal field theory which looks like Cardy, but it is not. So the G, just the size, just to be 2 to the 6. it's quite big. It's kind of understandable why it is hard to see such examples when you just look at small possible modular data and the small kind of classify modular invariants for that. But yeah, it exists. So I better stop now. Thank you so much.
Thank you. Do you have any question or comment? Yeah.
If you take two Lagrangian algebras that are related by one of these soft automorphisms, do the growth and decay rings of their module categories look the same, or can they be totally different? Do you know?
I better write it down. So, you want me to take two? So you want to take one Lagrangian algebra, just arbitrary, and then take this twisting of it. Yeah, even if it is a Cardi case, yeah, will be some difference in the categories of just modules. Yeah.
On the growth and decay ring level, or
on the growth and decay level, oh, must be. That's my feeling. No, I don't know. I won't be able to give you an example, but my sense is that they should be. Yeah. Because always coherences will play differently.
So I wanted to ask, I like this definition of Lagrangian better than I think the last time you spoke. You said about the square root of the Frobenius dimension sort of thing. I wonder, can you ask this question for like infinite, like for rep QG when Q is generic? Like what the Lagrangian?
This definition still applies. Yes, so the dimension goes to
so can you classify what they would be for infinite some data cases of infinite categories?
Have to confess, I was thinking about it, but it's not easy. So the only case which I had any success at all is so the infinite categories of finite dimensional are given in the algebras. So it's kind of a very comfortable many case, but so there, yeah, you can compute all commutative algebras, all Lagrangian among them, and the answer becomes kind of predictable one. You end up with even self-dual lattices sitting inside those abelian things. But that's all. It would be really nice to see the answer in general case, but yeah, my abilities.
You can't say what it is.
It shouldn't be that hard, but I just my skills are limited.
Do you have any other question or comment? If not, let's thank the speaker.